Okay, today we're going to do the fractals chapter, which is really more than fractals, but we start off talking about fractals, which are mathematical sets usually obtained through recursion that exhibit interesting dimensional properties. As you can see, what we're talking about here in the pictures, it has something that's called self-similarity. A shape is self-similar when it looks essentially the same from a distance as it does close up. Again, if you look here, we're blowing up this area here, and it looks the same as the entire thing. Same here, you have this whole leaf, then we blow up an individual leaf, and there it is, the same look. So we're going to skip this part here. We're going to get into the meat of this. We have something called initiators and generators. An initiator is a starting shape. A generator is an arranged collection of scaled copies of the initiator. So fractal generation rules. At each step, replace every copy of the initiator with a scaled copy of the generator. Rotating is necessary. So let's see some examples here. Okay, we're going to use the initiator and the generator shown to create the iterated fractal. So we'll start our first generation. Will look like this. And then our next generation would look like this. You can see each of these lines becomes this. And we could go further and further, but it would get a little messy, as if it pretty much already is. So essentially what we're saying is we start with the initiator, in this case a straight line. Then we replace it with the generator. And so what we do is we have our generator here. That's our first iteration. Then we go to the second iteration where we replace every line with the generator, every initiator with the generator. So again, we have the same principle here. Our initiator is simply a straight line. Our generator is a Y. So our first iteration would be this Y here. Our second iteration would look like this. And we could go further. And keep going in each iteration. So that's how that works. That's what fractals look like in a very basic system. So we use the initiator and generator shown to produce the next two stages. Now my drawing is not the best, so I'm not going to draw this. What we would do is take this generator here and produce 5 of them in here, and then we would do that again. That's much too complex for me to draw. So then we get to scaling dimension relation. To scale a d-dimensional shape by a scaling factor s, the number of copies C of the original shape needed will be given by copies equals the scale to the dimension power, or the copies equals s to the d. Using the scale dimension relation to determine the dimension of the Sierpinski gasket. So let's see. We have a scale of 3. We have a copies of 3. We have a scale that is 2 wide. And what we don't know is the dimension. So 3 equals 2 to the D. What I don't see is the formula for dimension. Again, we would have the scale here would be 1, 2, 3. And the copy would be 1, 2, 3, 4, 5. So according to our formula here, 5 equals 3 to the D. And again, we can't calculate D, which brings us to this. Scaling dimension relation to find the dimension. To find the dimension D of a fractal, determine the scaling factor S and the number of copies of the original shape. Then use the formula D equals the log of C over the log of S. So let's go back here. And the dimension D is equal to the log of C over the log of S. The log of 3, the log of 2. I believe in the homework and on the exam, this would be sufficient for your solution. You don't have to do this. You can calculate it. You should have a log button on your calculator. When you hit it, a parenthesis is going to go up. So put that 3 in there. Don't forget to close the parentheses. Then again, divide. Hit your log again, and 2, and close the parentheses. That'll give you the actual answer, but this is sufficient. So let's look at this one. The dimension would equal to the log of C over the log of S. So this would be the log of 5 over the log of 3. And that's it. That's all we'll need. That way, if you don't have a log button, you don't have to figure anything out. So the next topic we cover in this chapter is imaginary number, which is denoted, by an italic I. Imaginary number I is defined to be I equals the square root of -1. Any real multiple of I, like 5i, is also an imaginary number. So let's simplify square roots. Now, I don't know how many of you have had before or calculating square roots, but the square root of -9 is essentially the square root of -1 times the square root of 9, right? -1 times 9 is -9. So the square root tells us that we can do this, the square root of -1 times square root of 9. So I have to find here, the number -9 is I, and the square root of 9 is 3, and we would write this as 3i. Okay, now we get to a complex number. Complex number is a number, usually denoted z, which is equal to a plus bi, where a and b are real numbers. A is the real part of the complex number, and b is the imaginary part. So in the complex plane, the horizontal axis is the real axis, and the vertical axis is the imaginary axis. So what we think of in a Cartesian coordinate plane as the x-axis is the real axis, and what we think of as the y-axis is the imaginary axis. So let's plot the number 3 minus 4i. So we have 3 on the real axis, and we have -4 on the imaginary axis, And where they intersect, that is our point, 3 minus 4i. Okay, now we look at something with addition. So we're looking at 3 minus 4i plus 2 plus 5i. Essentially, the way we do this is we simply think of the I as a variable, in which case you would do this as 3 plus 2 minus 4i plus 5i. And we would combine the like terms, so that's 5. This is negative 4 plus 5, which is plus 5, and that's simply it. Okay, same principle on this one. 2 plus 5i, and we're subtracting 3 minus 4i. Now, the first thing you're going to want to do is distribute this negative, because we're subtracting this whole thing. So this would be 2 plus 5i minus 3 minus 4i, which would become plus 4i. So group in our like terms, 2 minus 3 plus 5i plus 4i, and this is negative 1 plus 9i. Now, this is the correct format. Do not write this as 9i minus 1. This is not correct. The real number or real part of the number comes first, then the imaginary part. Okay, this wants us to visualize the addition of 3 minus 4i plus negative 1 plus 5i. And first plot 3 minus 4i. So we have 4i, and that is here. The result is we're going to add 1. So we're going to go down one more, or go this way one more, to here. And then we're going to add 5i, so we're going to go up 5. And it's here. And this would be our actual point, which is 2 plus I. So let's do this the other way and see if we get the same thing. And 3 minus 4i plus negative 1 plus 5i. I'll have 3 minus 1, and I have minus 4i plus 5i. Plus 2 is what we have. Okay, now we're looking at multiplication. We're multiplying by an imaginary number. And this is just like any other thing like this. We're going to distribute this. So we'll do 4 times 2 plus 4 times 5i. And this is essentially 8 plus 20i. That's it. Okay, now we have to use the FOIL method. So let's do this. 2 plus 5i minus 4 plus I. FOIL method, FOIL. In case you forget, first times first. So 2 times 4 is 8. Outer times outer. So 2 times I plus 2i. Inner times inner. So 5i times 4 plus 20i. And last times last. Is 5i times I. So we have 5i squared. So let's look at I squared over here to the side real quick. This is what? The square root of -1 times the square root of -1 equals the square root of -1 times -1, which equals the square root of 1, which is -1 in this case. So I squared equals -1. This is basically by definition. Is I equals the square root of -1. Two definitions you'll need to remember. So let's look at this. This is simply 8. We'll take 2i plus 20i, and we'll get plus 22i. And this is plus 5 times our -1. And this is 8 plus 22i minus 5. Combine our like terms here, and we get 3 plus 22i. Okay, now we're going to multiply again. So I have 3 plus 4i times 2 plus 3i. And again, we're going to FOIL. First times first. 3 times 2 is 6. Outer times outer. 3 times 3i is plus 9i. Inner times inner. 4i plus, times 2 is plus 8i. And last times last, we got 12i squared. So keep this 6. Add 9i and 8i, and we get plus 17i plus 12 times -1. We have 6 plus 17i minus 12. Combine like terms, and we get -6 plus 17i. Okay, let's not bother with this. Or this. Or this. I didn't realize those were still in there. The next thing we're going to talk about is a recursive sequence. If you took MGF 1106, you've been exposed to this a little bit. So a recursive relationship is a formula which relates the next value, such as z to the n plus 1, in a sequence to the previous value, which would be z sub n. And in addition to the formula, we need an initial value, or z sub 0. Sequence of value produced is the recursive sequence. We're told, given the recursive relationship plus 1 equal to z sub n plus 2, where z sub 0 is equal to 4 terms of a recursive relationship. So let's start. We know z sub 0 is equal to 4. Let's look for z sub 1. Well, z sub 1, if n is equal to 1, then n is equal to 0. So this is z sub 0 plus 2, and z sub 0 is 4 plus 2, which is 6. So z sub 1 equals 6. Let's look at z sub 2. Z sub 2 would equal 2 minus 1, which is 1. So z sub 1 plus 2, which would equal 6 plus 2, or 8. Likewise, z sub 3 would equal z sub 2 plus 2, which is 8 plus 2, which is 10. And I think that's enough. So that's how that would work. Okay, next one is just a different relationship. We're using an imaginary number. So z sub n plus 1 equals z sub n times I plus 1 minus I. where z sub 0 equals 4. So z sub 1 would be z sub 0, which in this case is 4, times I plus 1 minus I, which would give us 1 plus 3I. So now z sub 2 would equal z sub 1, which is 1 plus 3I, times I plus 1 minus I. So this becomes 1 times I, or I, plus 3I squared plus 1 minus I. Well, this and this cancels each other out. This becomes negative 3 plus 1, or negative 2. So z sub 2 is equal to negative 2. Z sub 3 would equal z sub 2, which is negative 2 times I plus 1 minus I. This is negative 2I plus 1 minus I, which would equal 1 minus 3I. Z sub 3 would be 1 minus 3I. Now we look at z sub 4 and see what we get. We have room here. Z sub 4 would be equal to z sub 3, which is 1 minus 3I times I plus 1 minus I. Now let's do our multiplication here. And we get 1 times I, which is I, negative 3I times I, which is minus 3I squared, simply plus 1 minus I. So this is a negative I, this is a positive I, they cancel each other out. This becomes negative 3 times negative 1 plus 1, which is 3 plus 1, which is 4. So z sub 4 would equal 4. Now, one thing you can see here is we're back where we started. So this is simply going to repeat after this. Z sub 5 is going to be 1 plus 3I. Z sub 6 would be negative 2. Z sub 7 would be 1 minus 3I. And Z sub 8 would be 4. So that would just keep repeating those 4 values. Okay, next up is something called a Mandelbrot set. We're not going to go real deep into this. There are some interesting videos on YouTube that show the plotting of Mandelbrot sets. If you like to see some of this, you could just simply type in Mandelbrot set in the YouTube search engine and it will come up with several different videos. So, a Mandelbrot set for any complex number C. We define the sequence Z sub n plus 1 is equal to Z sub n squared plus C. We define Z sub 0 as 0. If this sequence always stays close to the origin, within 2 units, then the number C of a Mandelbrot set. If the sequence gets far from the origin, then it is not. So determine if C equals 1 plus I of a Mandelbrot set. So looking at Z sub 1 is equal to Z sub 0, which is 0. Squared plus I, which is essentially I. Z sub 1 equal to 1 plus I. And both of those have a coefficient of 1, so they're away from the origin. So far, so good. Okay. Sub 2. Now this is 1 plus I squared plus 1 plus I. So 1 plus I squared is 1 plus I times 1 plus I, and this is plus 1 plus I. So using our FOIL, 1 times 1 is 1. 1 times I is plus I times 1 is plus I times I is plus I squared plus 1 plus I. Now this is 1. This is plus 2I. This becomes minus 1. This is plus 1 plus I. So what happens here? This is 1 minus 1 plus 1, which is 1. But this is 2I plus I, which is plus 3I. So Z sub 2 is 1 plus 3I. And that is further away. Mandelbrot. That. Fortunately, that was quick. Let's look at this one here. Again, what did it say? Z sub n squared plus C. Z sub n plus 1 is equal to Z sub n squared plus, and defined as 0. So Z sub 1 is equal to 0 squared plus 0.5I, which is 0.5I. Is 0.5I. So Z is 0.5 plus 0.5I. Yes, I get 0.25I squared plus 0.5I. This is 1, so it's negative 0.25 plus 0.5I. And again, everything looks good. Okay, now this is where this gets a little rough. C3 is equal to C2 squared, which is negative 0.25 plus 0.5 plus 0.5I. I have, so we'll do this. Negative 0.25 is negative 0.25. And that becomes a positive 0.625. Now we're doing these. Oh, we're doing outer first, sorry. 0.25 times 0.5. That's minus 0.125I. And this here minus 0.125I. This becomes plus 0.25I squared plus 5I, or 0.5I, sorry. 0.5I. Here, let's see. This we have 0.25, 0.0625 times negative 0.75. Okay, I got this plus this, which is minus 0.25I plus 0.5. So this is 0.1875. This plus that is 25I. So these equal to negative 0.175 plus 0.25i. And you can see what's happening. We're getting closer and closer to the origin. So this is, I'm going to go with most likely. The calculation is more complex and smaller. We're going to leave the last one for you. I don't believe there's anything on the exam on Mandelbrot sets, but I do believe questions. We'll leave this last one. If we need to see more, we'll do it in the live lecture, or I can put a recording of it being done. But at this point, I'm just going to leave it there for you guys to do on your own. I'm pretty sure it will end up being 1 because it has the decimals. So when you multiply decimals, they tend to get smaller and smaller. So that's it for this. You guys have a good day, and I will see you next time.